All right, let's get started, everybody. Okay, let's get started. So I ended last lecture. I was kind of going over the last bit of logical effort sizing. As I mentioned, that's pretty much everything you need to know for homework 4. The thing I didn't emphasize too much of, though, is the branching effort. But there is another example in the slides that I'll encourage you to go over that includes branching effort. And all the work is shown in this one. So I'm not going to go over it in class here. But just so you know that is there. Today, I'm going to jump into static timing analysis, though. So static timing analysis, everyone has done FPGA design, right, in 125. It's also used for FPGA design. So it's used for ASIC design, FPGA design, and it is probably the most undervalued part of chip design because it impacts your RTL development, impacts your placement and routing, impacts your final sign-off. Basically, this crops up everywhere in design. And there's entire jobs at companies that are static timing engineer. I know one of my master students just interviewed at Apple for that position. So it is it's a very important area with lots of work needed on it. Now, what we're going to talk about is you learn a little bit about timing in like 100, not kind of, I call it unit delay time. You learn what setup and hold are a bit. But we're going to delve into that a little bit more in depth, and then how that relates to static timing, and how you can actually make sure something works in practice. And this is actually going to span 2 lectures, so today and next Tuesday. And I will also do a demo on Tuesday of the static timing in OpenRoad. So there's a tool called OpenSTA, which it's legitimately a commercial tool that was open sourced. So it was a company, I think it was called Parallax Design Automation. So it's a startup company. Every startup company in the EDA area essentially makes their own static timing tool. But they all use a standard set of command interfaces, which are based on the Synopsys design constraint language. So these are the same ones that are used by Synopsys tool called PrimeTime, which is the standard timing analysis tool in the industry. So the good thing is you learn the open source one, you can basically learn how all of them work. So it's very good for that. And then we'll talk a little bit about timing corners in more detail. The demo I can give and the tutorial I have on the website does some more stuff with timing corners. So, why clocks? I know there's one group in 127 that's talking about doing asynchronous design without clocks, because clocks are the problem with all design, right? And if they can make or break a chip, basically. But the real reason is it's easy to understand synchronous design, because you're basically taking time, you're dividing it up into clock periods, and then it's a discrete thing, right? You just do one clock period, do another clock period, and certain things happen in a clock period. When you do this at known event frequencies, it simplifies the problem of building state machines. Imagine if you had to think about a state machine that could transition states at any time when any input signal changes. That'd be hard to verify. And because we do this clock period thing, we don't have to worry really about the variable delay through combination logic. So if you have a block of logic, some paths are longer than others, some are short, right? They're different lengths, and depending on which inputs change, the outputs change at different times. And with using a clock period, you just say, I just need to know the bound on it and make sure it works. Now, the other reason we don't do anything with asynchronous design in industry usually is no one learns it. It's hard to teach, it's hard to debug. There aren't tools for it that work very well with it, and so it's hard to use in practice. The group that's doing asynchronous design is like, oh crap, what do we get into? So we're going to talk about this, and there's kind of 2 high-level things. You can think about clocks in terms of state machines. In the lower left here, you have combinational logic with a register that's your current state, and it feeds back to the next state. And you might have some inputs here as well, to change the state. So this could be a Morrison state machine, a Mealy state machine. It could be a combination of many different state machines. You also have register-to-register timing in your data path. So if you're going from a pipeline stage to another pipeline stage, that's not necessarily a state machine, but it's you're passing data between things. And you need to check that the clock synchronizes all of these things. Now, the general idea, starting from mile high, and most of this should be reviewed starting out, is that the cycle time is determined by the delay through the combinational logic, CL. Your signals have to get to whatever's going to capture it before the clock edge. Now, I also kind of interchange latching edge, flip-flop, or latch. So we know flip-flops are edge-triggered devices, latches are level-sensitive. Very few people use level-sensitive in designs, but that isn't. You can do static timing on those as well, but we're going to mostly talk about this in context of flip-flops, because that's the simplest to understand. And then so these latching edge, you can have positive edge, negative edge, so you can have inverted clocks, things like that. And you basically need to ensure that the cycle time, T-cycle, is going to be greater than the propagation delay through your logic plus any overhead. And this overhead can be a number of different things. Sometimes they'll add overhead that's called guard banding, just in case. If it ends up being a really hot chip, you want to make sure it still functions. But you want to minimize this overhead because it eats into your performance. If you think about Pentium 4, it's old now, but it'd be 3 gigahertz. It would have a cycle time of 333 picoseconds. So you divide that up into your data path through your logic delay and your overhead. And you can do a bunch of things to change the cycle time. One thing is you can rewrite your Verilog, restructure it, add pipeline stages. You can change parameters to tools. So like this Yosis, you can have it run a different set of scripts to get different results. When we start talking about buffering and sizing in the tools, we talk about how to do it and evaluate it with Elmore delay and stuff. But the tools have algorithms to do this, and you can change what they do to get different results. So you can change the timing at many different points along the flow, but you need to evaluate it at all those points. Now, pipelining, you've seen this in 120 and maybe a little bit in 125 too. But basically, you can divide things up into smaller stages of delay. Just to point out, if you have some sort of logic here, A and B, and it has some propagation delay, PD, you can split it up into 2 components, and then you're going to be limited by the worst of these. So one of them will have some delay, the other will have another delay, and you have to make sure that the maximum delay between all pairs of registers in your design is less than the cycle time. So in this case, if you divide them perfectly evenly, you could get twice the speed, minus a little bit of overhead from this extra register overhead. We'll talk about that as well. So the more pipeline stages you have, you can get better performance. You hit a limit, though, because at some point, you can only kind of move single gates across a pipeline stage, so you can't move part of a gate across. And also the overhead of the flip-flops actually eats into your margin too, because they have a setup and hold time which you have to obey. That adds to the overhead part of this. So now let's kind of think more about critical paths, and we're going to also talk about setup paths first. And if we have kind of an example here, we have a launching flip-flop on the left over here. This is going to send some value in here. All these other values are going to be coming from some other flip-flops or primary inputs to the circuit. They could be coming from off-chip too. Yeah. The overhead delay, I'm going to get more into it, but the overhead delay is stuff related to setup and hold of flip-flops and clock skew and some other things. I'll talk about those in detail in the coming slides. So if we look at this, so all these inputs that are not shown are just to other launching D flip-flops, somewhere else, or inputs or outputs of the circuit. So we're kind of looking at one path here, which is from one launching flip-flop to a capturing flip-flop. And these also may have fan-out. Like this may get reused somewhere else in other logic and go to another flip-flop. So there's a lot of overlapping paths that can be doing different things, but we're kind of extracting one path here with the logic between this launching and capturing flip-flop. And when we look at this, we need to make sure that this path works. Okay, so in this case, the longest path through this might be this purple path that goes through 5 gates. And the delay of that path depends on not only the gates themselves and a little bit on the number of gates, but as we've seen, the delay of gates can be very different. If you have a very complex gate, it can be much slower than a simple gate. So just number of gates is not sufficient to know what will be critical. So we'll actually use the gate delays themselves to determine criticality when we find a critical path. But also we talk about wiring. Wires actually scale worse than gate delays in modern technology, so we have to include those as well. And if there's a very long wire in this path, like it could be that this path is the slowest path because this wire here goes halfway across the chip. You don't know, right? It goes halfway across the chip and comes back. It's a horrible route. So you need to include the gate delays and the wire delays in your analysis. And this is what static timing will do as well. But basically, to make sure this works, you need to make sure that you have your cycle time here, you have a rising clock edge, and then the next rising clock edge gives you your capturing clock edge. And you want to make sure that you can send something from Q1, it can propagate through all these things, and it gets here at this other flip-flop before the next clock edge. Because these are sharing the same clock signal, right? Now, not only does it have to get there, but it actually has to get there a little early. When you arrive to a meeting, you don't want to show up on time when the meeting starts. You want to show up so you can have your seat, get set up, put on your headphones for Zoom, whatever. That's your setup time, right? You have to get prepared to do stuff. So you have to have some sort of setup time at the capturing flip-flop as well. If you should have talked a bit about this in 125, where if something arrives later than the setup time, it may be unreliably captured. And so it has to arrive at least a setup time before the capturing flip-flop. That's part of the overhead. Okay. Every capturing flip-flop has a setup time. That setup time is actually not a constant too. Remember I talked about the libraries and the delay tables and stuff? When we go into the libraries, there's a table for setup time. What does that table depend on? It actually depends on two things. So this is a little bit of a tangent. It depends on two things. It depends on the slew of this input signal and also the slew of the clock. So where gates depend on the output capacitance and the input slew, the setup time of a flop depends on two slews, the D input and the clock input. And as you might suspect, if you have a slower transitioning clock, it's going to probably have more setup time. If you have a slower transitioning input, it's probably have more setup time. If you have crisper ones, they'll have less setup time. That's the general trend. But it depends on what type of flip-flop, really. The point being, it does differ. And so you have to make sure that it arrives at that setup time before the clock to be reliably captured. Another thing is, I drew that in kind of a nice way where we had clock, and then I labeled T clock 1 and T clock 2. Technically, every flip-flop on a chip receives a separate clock. What do I mean by separate? It's a different wire. It may go through different buffers, right? When you actually implement this, there may be a buffer here, there may be a buffer here. This wire might be really long. And when you then go through buffers and wires that have different delays, T clock 1 does not equal T clock 2. They're offset. That is clock skew, right? When you have, it's supposed to be the same clock, but it's offset by some fixed amount, and that also adds to your overhead of your path. And so it depends how you define it. Usually it's the receiving clock minus the launching clock to define skew, but there's no standard. It's just the delta between the two. Yeah.
So if we want to synchronize everything across the chip, why do we have this in place?
If we want to synchronize everything across the chip, why do we have this in place? You mean why do we have the different clocks? Or?
Yeah.
Well, think about it this way. You have one signal coming on chip, and it has to go 100,000 places. How do you do that? It has a fan out of 100,000. That's a big delay, right? Technically, you could make a very big clock driver. This is actually what they did until the early 90s. I'll talk about when I talk about clock distribution, but the problem is the driver becomes too big. I have an example that I talk about. The company that did it until the early 90s was called DEC, Digital Equipment Corporation. I think they were ultimately bought by Intel, but it was their Boston design group. They would have a single driver methodology. Guess, we know how big transistor widths are, 150 nanometers, 0.15 microns. So this was back when technologies were when was it, 1.2 microns. So that was the width of a small transistor. Guess how big the width of their clock driver had to be? It was like a centimeter. So they would have a centimeter, take a centimeter, divided by 1.2 micron. That's how many fingers they would have on the clock driver to drive the clock tree. And it was just interdigitated, put it along the side of the chip, and it drove everything at the same time. Super inefficient. You can look at the chip and be like, there's the clock. Without glasses, if you have a hard time seeing, you didn't see it. So it doesn't scale. So what they do is instead you have to do a clock tree of some sort. I do research on clock meshes, which reduce variability. There's a bunch of different techniques you can do. And I have an entire lecture on that in a few weeks. But none of them are perfect, and you end up with skew. Skew is a fact of life. And that skew can be due to a number of things. It can be due to, as I mentioned here, different buffer sizes, different wire lengths. It can also be due to variation. If the voltage on this side of the chip is a little bit less, it's going to be slower. If the temperature changes, the skew can change.
In that technology, did they eliminate the skew completely? Or
Back then, did they eliminate skew? No. They did not eliminate skew completely. There were still wires. You still had to go from these giant drivers to the actual latches, and that was still different. But not as different as having a buffer tree. Yeah. Let's reserve the clock stuff till later, because I have a lot to say about that. But there's a lot of things you can do, but it's a very hard problem. It's almost analog design, because there's so many different criteria. Digital stuff, you were basically concerned about power, delay, and area. That's what you want to do. Is it correct? Power, delay, area. Analog, you're suddenly worried about noise, variability, kind of all sorts of other things. So it's not an easy answer. But here, you basically have these two clocks, and you can see up here at the top that they are not the same. They're offset by a small amount, even though you intended them to be the same. Now, that can be good or bad. You have to add that to the overhead. But now, which clock is early and which is late, right? In this case, if clock 2 is delayed from clock 1, that could actually be good, right? Because you launch on clock 1, and then it goes through the data path, and then clock 2 is actually a clock period plus a skew later. So you actually have extra time. Great, right? Well, that can be bad for the things after that last flip-flop, because it's delaying the launching out of clock 2, so whatever's next is going to be delayed. So it ends up being that it can improve things by having setup times by having positive skew like that, but it can be bad for other things later. Now, if we had negative skew, let's say it came in here, and it was maybe instead of coming from the left just pictorially, the clock came in here, and it went to this one first, and then had to go over here. So the opposite. You could have negative skew there, where it arrives at clock 2 first, and then it arrives at clock 1 later. That essentially is negative skew. Now, what it means, though, is you're going to have one clock pulse that launches on clock 1, and then the next clock is going to be a clock period minus the skew earlier, so that this path has to be faster by the skew amount. So it adds over. It can go either way. So it's not always, positive stuff. So now we have not only the setup time, but we also have the skew. So these are both the overhead. We have another overhead, which is the clock to Q delay, or the launching time of the flip-flop. So when the clock arrives at the first flip-flop, clock 1, the data on the output doesn't change instantaneously. If, for example, it's going to keep the same value, it basically is effectively already there. But if it's going to get a new value, it has to capture the previous value and propagate it to the output and change the value. That takes time. Inside of this, if it's a master-slave latch or something, the first stage of that already has the value. You need to transfer it into the second stage for it to be on the output. And that's called the clock to Q delay of the flip-flop. So it's the time that it takes to become valid on the output. That's basically how late start do you get. If it's a track race and everyone's lined up at the starting blocks and takes off, who takes off the fastest is your clock to Q delay. Then the rest of the race is the path delay. Then, I don't know, you want to arrive earlier, as early as you can, I guess. There's no setup equivalent race. But that's also an overhead. So you have to add that third part in here. So all of these together now are the overhead of the path that are actually not the path delay itself, right? The path delay is Tmax. So that's kind of review stuff. Now, what's the good part about this? Well, what if I have a path, I have a critical path, my chip doesn't work very well, or it doesn't work, it's too slow. My period's too slow, and these all add up, and it doesn't get to the capturing flop at the right time. What? Slow the clock down. Instead of running at 100 megahertz, run at 99 megahertz. That's a solution, right? You can run everything slower. What if it's USB that runs at 48 megahertz? USB 1. Well, you can't really slow that down, because then it's not really USB anymore. It'd be a Alibaba Express USB controller that runs at 47 megahertz. And half the time you plug it in, it works, half the time it doesn't. So some standards you can't slow down, which is a bad thing, but some you can. If you buy a chip from Intel, AMD, NVIDIA, you're going to buy a chip that runs at a given frequency. And you're going to pay more for the 3 gigahertz chip than the 2.8 gigahertz chip, because that one happened to have a path and enough overhead that or less overhead that it actually work at that speed. They do what's called speed binning, and they say we'll sell them at different speeds that we know they work at. But with USB, you don't speed bin USB, so you don't speed bin standards. But you can change that with the clock period in some cases. There's actually a problem though. Hold times are actually more challenging than setup times in industry. And what is a hold time? So in this path, I kind of have this little black path here that's shorter. It's four gate lengths instead of 2. That's the fastest delay through the logic. So there's redundant paths, right? There's reconvergent logic. It branches out right here, and then it reconverges on this gate. And the delay from here through this and the delay from here through this are different, with the top one being less than the bottom one. So there's cases where you can have a faster delay through this, depending on what the inputs are. Now in this case, you're going to have the same thing. You have a launching clock on clock 1, you're going to have a capturing clock on clock 2, but you want it to basically keep the same value after clock 2 by a certain amount, so that it can be reliably captured. Another way to think about the setup time and the hold time is it's a window around the clock edge where you can't have the input change. It can't arrive too late, it can't change too early. It has to stick around to be captured. And so for this, you basically have the minimum delay has to be greater than the hold time. Right? So you have to go through here, it has to be greater than the hold time. And the key here is that you don't want it to race through, because in a setup time, you want it to be captured by the next clock edge. You get a full period. With the hold time, you don't want it to arrive too early that it gets captured by the capturing clock edge on the same clock edge that it launched from. That's the key difference. Same clock edge. They're not exactly the same though. They're skew, because they propagate around, but they're intended to be the same clock edge. And so if we write it like this, here's one clock. If I show clock 2, let me do it like this. Clock 2 might be like this, right? So it's still, let me draw it. It goes down here. So it's a little skewed, right? Now what that means is this period between here, which is between the rising edge of clock 2 and clock 1, if it were able to go from the launching edge through all the logic and get to that capturing one in that tiny amount of time, it would be too early. Because it's the same, we intend for these two clock edges right here to be the same ones. Oops, I just deleted something. Right? Now, think about it. What is the fastest path you can have in logic? No logic. What if you have a flip-flop going to a flip-flop? There's no logic between it. Why would you have that in a design? Synchronizer, shift register. There's a lot of reasons you could have it. It could be technically a shift multiplier, right? It can be useful. So you can have a flip-flop to flip-flop path, no logic, and a short wire. That's the worst possible case. If you have any skew there, then you'll have a hold violation, and you may capture the value too early and get the wrong value. I have to say, the first 2 chips I made with the open source tools didn't work because of that. Actually, the first one, everyone's chip didn't work, because it was actually a scan chain around all of the IOs to basically configure the IOs into like input or output mode. You couldn't run that scan chain because it's a scan chain. You serially scanned in all the bits, configure the IOs. It didn't work because there's a hold violation, so you couldn't scan the values in. You couldn't use the input output to the chip. Brick. That's an example. Now, what can you do about that? Well, setup time, you can change the clock period. What can I change with the hold time? I have T minimum, I have T hold, I have T skew. Do I control any of that after it's designed? No. So literally, it's a paperweight. That's the one I passed around. I was like, okay, people can touch it, whatever. It's a paperweight, a very light paperweight, though. So that's why hold times are actually more serious than setup times. They're also pretty much more prevalent as well. You have lots of flop-to-flop paths with minimal logic. If you look at a general design, there's just so many of them. What do you do to fix it then? Add delay, add buffers, make the wires longer. You could fix the skew. If you also fix the skew in your clock tree, that can also improve your design. I do see a lot of people push through designs and it has hold problems. This is actually what happened in the last time I taught this class. The project was to push the performance of this RISC-V processor I gave them. It was one that wasn't in a lot of open source places, and I gave it to them. I said, set up the constraints and see what you can do to make it work fast. Everyone had hold time violations. And so it was actually making it work at all that was the problem, because the clock was actually really bad. The problem is they had a positive clock and a negative clock, and they had paths between the positive and negative clock, and because they were 2 different clocks, right, one was inverted, there was high skew between them. So there's a lot of hold violations. Now, so the minimum path delay is the hold time. And then just to review, we can think about that as a window where you have setup time before the clock edge, like here. You have hold time after the clock edge here, and you want it to be stable around the window. So setup time, hold time, setup time, hold time. Every clock edge. Now, what does it mean when I draw these things like this hash like this? That means this signal could change as early as this or as late as this. That's a way that they demonstrate the window of logic changing. So my earliest path is that first cross hash, my longest path is the right. So that's the range of min to max delays through that. And so when you start to see timing diagrams, you're going to see that window. So it's not a single switching anymore. It's that it could switch anywhere in that time. It could go low to high or high to low. That's why it's meant to illustrate the timing and not necessarily the logic value. But you could see things where, if you get rid of this and you get rid of this, that there's some unknown value and then it settles to low. So you may see diagrams like that as well. Now, I already kind of mentioned this positive and negative clock skew. So positive skew is good for setup violations because it effectively lengthens the clock period. It gets added to the clock period. But it's bad for but negative skew is bad for setup violations because it's subtraction of the clock period. It's opposite for hold. If you have a positive skew, it actually it improves the hold time because it moves the clock further out so that there's more time between the launching and that same edge on the capturing. So, but it's bad the opposite case. So they're kind of opposites of each other. In general, for that reason, it's hard to predict where it will benefit you and where it will be a disadvantage. So they just try for low skew. That's the first goal. Try to get rid of skew. But when we actually evaluate designs, we can't ignore it. So get as small skew as you can, and then check where it might still be a problem. Now, why don't you just say, oh, do everything you can to get a zero skew? The problem is it consumes power. That deck thing, that had very low skew, but it had a 1 centimeter buffer driving your entire chip. It was super high power consumption. So you don't want to generally over-design it. You want to design it so it's good enough for your design and then you don't have problems. Now, just to illustrate, these are kind of illustrating the same things I've already talked about, but with timing diagrams. If here we have a launching flop, register A, a capturing flop, register B, and then we have two clocks, clock and clock prime. So in this case, clock prime is the launching one, and clock is the capturing one. And we see that there's a little bit of skew here. So the capturing clock arrives a little bit, or starts a little bit before the launching clock. So that would be negative skew. Again, I'm not going to hold you to the definitions, but usually people say the capturing minus the launching, so it kind of depends on your perspective, what it is. I'll be clear when I tell you things on problems. So in this case, though, the capturing clock transitions before the launching clock. And you can see here that launching clock will cause this input to the combinational logic to change. And then during this period, there's some delay through this, and this is your longest delay here. There could also be an early transition here, where it starts to transition, and you could draw that in here, but it's not shown for the sake of illustrating a setup violation. But right there, I'm just kind of pointing that out. So the latest arrival time is it settles at this point, and you want it to arrive before the capturing clock. But here you can see it's arriving basically slightly after it. And so that's a violation. Oops, actually I drew it to the wrong clock. Let me be very clear about this. The capturing clock is CK, so it's after that clock. Right? What you can clearly see is before the value settles on the output of that. And this doesn't include the setup time. This is just kind of saying, oh, there's zero setup time. All right? Now, what about a race through time? So hold times are hard to grok when you first get it. And that's why I want to kind of illustrate it. Because they're more important, because they're a little less intuitive, that's why I kind of give another example of it. In this case, we have the same thing, except CK. So this one, CK was early, and here CK is also early. And this launches out of the first register. Now, this is the earliest time here that the output changes. So this is the clock to Q delay. And then notice that this is the earliest time that it propagates through the logic. So that'd be that short path or no path. If there's zero logic, it'd just be a wire, right? And I would equal O, or O would equal I with just some wire delay, right? And then the problem here is that this came early enough that's before this clock edge, which it was intended that these are technically the same clock edge. Logically, they're the same, right? But timing-wise, they're different. I intend cycle by cycle that all the things transition on those sets of edges. That's another way to phrase it. But they're just different enough that it got captured a cycle early. So what happened? Well, I had a value come into the first register and then go to the second register. It was captured in both of the registers at the same time, the same logical clock edge. So it raced through. And I did not store the value that was originally in register A into register B. Okay? So that's the big problem. Now, what did we do when we tried to do things when we had this scan chain that wasn't working on our chip? There are some things you can try, but they're not very practical. How can you slow logic down external to a chip? Well, you can't change the clock because that's the period, right? It's not the logic. You can turn down the voltage. We tried running the chips at like 1.3 volts, 1.2 volts. They were made for like 1.8 volts. If you run it at 1.3 volts, if there's any buffers or logic, it's going to be slower. And so it'll potentially make these paths slower. The problem is it can sometimes make the clock skew worse. You don't really know. So we tried to slow it down. We also tried to pad data. So let's say you shift something in and you don't want it to skip a register, so you can actually insert dummy bits and say, well, okay, maybe this one can race through and so on. There were some hacks to get it to work. And some of them got to work, some of them didn't. But it was very hard to get it to work. So timing constraints. So we kind of revisited this. You should have seen some of it before, but now we have, in addition to just setup and hold time, we have a couple things. We have clock skew and we have clock to Q delay as well. So the launching time of the flip-flop. And then we also have a maximum delay and a minimum delay of a path. So those are different than you've probably seen before. Usually you just think of the delay, but now there's a range of delays. And those are going to have different checks that we're going to do to make sure the chip works. All right? Now, we've talked about skew. We've talked about how you can have the same logical clock, but different timing clocks, right, because they're skewed. There's no real term for it. They're all still referred to as the same clock, but they're just skewed. We can also talk about things that are called derived clocks, so clock identification. So this definition right here is important. What is a derived clock? A derived clock is something that starts from the same clock source, but then is modified. It could be, for example, that one example I mentioned for the project last year, where you just invert the clock, and now I have a positive clock and a negative clock. Technically, those are the same clock, but they're 180 degrees out of phase, right? 180 degrees out of phase plus a little bit of skew, and that skew depends on how many things they fan out to. If you have the negative clock that fans out to, say, 1,000 things, and the positive clock fans out to 90,000 things, they're going to be made from trees that have different delays, and there's going to be a lot of skew between them, unless the clock synthesis pays attention. You can also have things like clock gators. So here's an example of clock gating, where you can have a gator is just it's basically an AND gate. It could be a NOR gate, an AND gate, it could be any logic, and you would have some enable signal right here that turns this on or off. And actually, this is a different example. This is a couple examples. So if you have an enable here, and it were to go low, it would disable the clock here on this capturing flip-flop. Right? So you don't have a clock that toggles there, and it turns it on and off. Enables are frequently used to save power, because if you don't toggle something, it'll use less power. But that AND gate can have different delay than some buffer, and so you'll end up with some skew too. This is also illustrating another example of you can have two clocks come in, and you could have this, they could start from the same thing, and this could be a divider. It's essentially a counter. A clock divider is a counter where you just look at the overflow bit. So you count up 8, if it's a 3-bit counter, you count up 8 things, and when the carryout changes, that's your clock pulse. And so if you do a 3-bit counter, that would be a divide by 8 clock. And then you use that carryout as your downstream clock. So if you tie these two inputs together, then you generate some clock here. Actually, this example wants them not to be tied together. This is related to this, except they're different by a factor of 8. Right? For every 8 toggles of clock 2, you have 1 toggle of clock 3. They're different frequencies, and they might also have skew between them as well, depending on the delay difference between the edges. Like if we think about that, like if we draw it here, let me just do a 4. Well, I'll do 8. So here's what, 1 period, 2 periods, 3 periods, 4, 5, 6, 7, 8. That'd be one transition, oops, or half a period of clock 3. This is CLK2. And it would go low here. And so you can see that what would happen in this case is the duty cycle is different, but these clock edges might still line up here and here. So don't confuse the skew. They might have very low skew if those edges line up, but they could have different multipliers, essentially. So that's a derived clock where you then have to do, then you could basically, if you have clock 3, you could have a data path that has 8 times the logic in it than something driven by clock 2, right? Because the time of the period is 8 times. You can have derived clocks, you can have divided clocks. You can also have clocks that are asynchronous, they're unrelated. Those are very difficult to deal with, but you then need to set up timing constraints for all these things. So if you were to have something like this, the timing check, since it's using a divide by 8 clock, the combinational logic can be 8x bigger than the other case. So this is saying that the T of this thing is actually much bigger. Right? So the point of that is multiple clocks. We actually don't have a lot of time in this class to talk about multiple clocks and clock synchronization, but you'll get some practice at dealing with it in the capstone, for people in the capstone, when you start to have different clock domains. At the least, every chip has a clock that comes on chip, and then you have some sort of a divider multiplier to generate a clock of a different frequency. That's kind of a bare minimum. Sometimes a lot of chips will have an off-chip clock as well as an on-chip clock made from like a ring oscillator, like we saw the last lecture. Right? We have a ring oscillator on chip, and the nice thing there is you can basically use that ring oscillator and turn off your IOs and your external crystal and so on so that you save power. So that's a case that's very common in chips designs. You could have different clocks. You're making a VGA display that goes off chip. VGA displays have to have a 25 megahertz signal rate. So you have to make a clock specifically to adhere to that standard. Or USB, 48 megahertz, we're talking about that. So sometimes you have clocks that are frequency because of a standard, but then you still have to have them interface with your main system clock. And when you have things that go across that, you have to deal with arbitration or handshaking to make sure that you reliably transfer data. Static timing will also check that those things can be done to some extent, but it actually does not do a good job at that. You have to have different tools to do clock domain crossing analysis. Yeah?
For like the deep flip-flop, when would we use, like having the derived clock, when would we have something like that go inside of the clock versus having it go inside of the enable pin for a deep flip-flop?
Oh, I see what you're saying. So you can take, you're asking the difference between having a divided clock versus having a flip-flop with an enable. They're kind of interchangeable because internal to the flip-flop, you implement them almost in the same way. The enable and a flip-flop will typically gate the clock, sometimes. You can come up with substitutions for each one. I guess the other thing is it changes some of your, what do I want to say? It changes whether you put the overhead on your data input or your clock input of a flip-flop. So we talked about this equation for setup time or hold time, let's say. Here, if you add some enable logic, if you add an enable to the data path, it would be on this side of the equation. If you add a clock gator, it's probably going to be on this side of the equation because it's going to eat away at your clock period. They're equivalent though, right? So, all right. Now, so that's basically what we have to know for timing analysis. So let's take a 5-minute break, and then I'm going to start introducing static timing and what that does. I know it breaks a little early, but.
Since our chip is going to be asynchronous,
All right, I think it's like 3 or 4 minutes. So, okay. So we're gonna talk about static timing now. So first thing is, what does static timing get used for? It's actually quite a few different things. First of all, the question, can my chip run at some frequency, X gigahertz? That's kind of the standard one. How do I make it fast as possible? Does it work at that speed? It can also identify parts of your circuit. So if it runs at 3 gigahertz, what path is the path that's limiting the operation at 3 gigahertz? Or it might be multiple paths. Right? You can have several equally critical paths that all determine your performance at the same time. Also, as I mentioned, the hold time checks. Will my chip work at all? Because if there's a hold time problem, it will not. So those are kind of the standard questions that most people ask. How does it kind of do this? Well, the key thing to static timing analysis is the keyword static. So static means unchanging, right? It doesn't change. Well, how do you measure timing of signals transitioning if nothing changes? What does that mean? Well, what we're going to do is we're going to consider the worst case of all switching simultaneously. And so that's what static means, is considering everything at once. The alternative is dynamic timing, which is actually to run a simulation and to see if it works. When you do designs, and in the capstone class, for example, you will do dynamic timing evaluation, where you'll take your Verilog design, synthesize it, have the gate level Verilog, go through all your layout. Now you have delays of your gates and wires. You can actually annotate those back into your gate level Verilog and run Verilog with delays. Frequently, people do this also. The problem with that, though, is you can't test all of your critical paths. Like, how do you come up with the combination of inputs that sensitizes the one path that's the worst in your design? Maybe that only happens in one special case, where you have an interrupt within an interrupt on this instruction. You can't ensure that you're going to actually hit that criteria to actually test it in your dynamic simulation. So for that reason, dynamic timing analysis is used mostly to be like, will it boot up? Does it seem to reset properly? Kind of fundamental things. It's more of a sanity check than anything else. It's not used really for verification. So the alternative, and if you think about it just from the number of inputs, like if you have n inputs and m flip-flops, and so you consider those flip-flops as inputs, you have to consider 2 to the m plus n minus 1 possible states and transitions to next states to figure out what the worst combination is. You can't feasibly test that for any reasonable size of number of inputs and number of states. So that's why we have to do static timing analysis. The other thing is, I mentioned every startup company has their own timing analysis tool. You'll do timing analysis sometimes in synthesis, you'll do it in routing, you'll do it in placement. Depending on what you're doing, you want to optimize it for timing. And so you also need to know then, if the timing is a problem, how do I fix it? The way a lot of the optimization tools work is pretty rudimentary, really. Like, it'll do placement, and then it'll run it without wires, just assuming wire lengths based on how far apart things are, and then say, okay, what's my worst path? Let me move this gate. How does it affect my timing? It's on my critical path. If I move it here, does it get better? Okay, keep it there. Now if I move this one, does that work? Okay, keep it. And so it literally does a lot of kind of informed decision making. It'll look at your critical paths and try to fix things on the critical paths, but the way it evaluates whether it improves the timing or not is it tries it, and it reruns timing. So because of this, we have to have a thing called incremental timing, which actually doesn't rerun the timing everywhere. It only reruns timing on parts that change. And that's a key component of static timing. Is it can be used for sign-off, like the top things, does that happen? Or incremental, where I want to improve my design and measure the delta in improvement. A lot of times this is within a tool, right? Yeah.
So in the process of a tool doing that, is there any level of like randomness or rerun the tool multiple times to get different results?
That's a very good question. When you do that, is there any level of randomness that you get kind of different results? The answer is yes. Usually that's a bug in the timing analysis tool. Sometimes it's very hard to replicate. You want it to give the same answer all the time, but something can sometimes change and give different results. Usually it ends up being like rounding errors that then affect a decision that then change your result. I know I've seen a couple bugs in open source tools related to that. Like actually, they had one that's not really the timing, but when you let's say you move a gate, and if you do this during detailed routing, like with global routing, you move a gate, you have to reroute the wires because it's in a new location. Okay, you route those wires. If it's good, you keep it. If it's not good, you want to undo it. You move it back. There's a bug where the router will not give you back the old route, so you can sometimes get a different route. So that's a case where you can't quite undo things, which would result in differences. Not necessarily the timer, but in the optimizer. And that was a thing that existed in the tools until like last month. Open source tools. You didn't see it happen very often though. And then, in addition to that, you also have corner analysis. This last one is also called, related to the first item, it's basically timing sign-off. So sign-off is when you want to basically ensure that it works over a bunch of different environmental and manufacturing conditions. This could be, I want to work at high temperatures, low temperatures. I want to have it work at high a little bit, if my voltage supply is supposed to be 3 volts, I want to still make sure it works at 3.1 and 2.9. Because I might have a power supply that fluctuates by 10%. It could be the process. I've mentioned, like, if you manufacture one day, you have faster PMOS. And on that batch of chips, you want to make sure it doesn't fail. So it's kind of this corner analysis to make sure that it still works under a bunch of different scenarios. And that's also important in timing analysis. So the key thing, so we're going to start thinking of a circuit as not a netlist. So we're used to seeing kind of the view on the bottom left where we have logic gates, they have inputs, outputs, wires connecting between things. I'm going to kind of ignore wires in most of the stuff, but they can basically be represented just like gates in ways where you have input and output. And so a lot of these examples will exclude that. But you basically want to break it down such that all of your primary inputs on the left become nodes in a graph. You can envision these coming from a single node, but that's not really necessary. For visualization and for some of the graph algorithms, it might make sense. And then all of your primary outputs of the circuit end up becoming nodes as well. And then for every gate, you want to have a node that's an input pin and an output pin. So a 2-input gate will have 2 input pins and an output pin, and edges between the inputs and output pins. And then, in this case, if you have this example here, this primary input to G1, this would actually be a wire edge, right? It's connecting an input, which could be a pin somewhere on your design, to the input of a gate. Now, I want to point out that this is kind of a generalization where this output may actually go to an output, or it may go to the input of a flip-flop, like this. This over here might come from off-chip, or it might come from a flip-flop. But what we end up doing with static timing is we divide the circuit at flip-flops as the boundary of the timing. And so we transform it into a graph like on the right, even if it has flip-flops. Now, why do we do that? Well, if we didn't, we could have cycles. Like if you have a state machine, you have a cyclic graph where the output edges could go back through gates to the input of the flip-flop, and now that's hard to do graph algorithms on. How do you find the longest path in a cyclic graph? That sounds like a Google interview question, right? The answer is it's hard, and you don't want to do that for static timing. Now, the only difference is, is how you set up doing the timing analysis with these flops versus inputs and outputs. And I'll talk about the details of that. So yeah, the edges are gate or wire delays, and then the nodes in this graph are pins of gates or inputs and outputs. All right? So we can represent any graph like this, and then it becomes a directed acyclic graph if we break it where we have flip-flops. So no cycles, which is good. Skip some things. What are the delays on these edges? We had the library lecture. We have delays for our logic gates. They are values from the tables in the lib file. If you have an input slew, now you at least know this for your primary inputs, and you make a guess for them for your outputs of flip-flops. You look up the input slew and the output load, and you can figure out the delay of the gate. So I can add this delay to any of my edges in the graph. I can also add a slew rate to a signal on any of those in addition. I'm going to also kind of ignore slew rates for the most part, but usually when you talk about static timing, you're talking about signal times as well as their transition time as kind of a pair of values. And those are used in these tables, obviously. So you've seen this. This is how you get the cell library stuff. How do you get the wire delays? Well, we went over Elmore wire delay, right? That's a first order model. You can do something like this. Now, this may be information from placement only where you don't know wires yet. And what do? Well, they'll say, oh, this pin is this far from this pin. I'm going to assume it's that long of a wire. So it's just based on distance, like in placement. Or global routing is a stage where you kind of do the general region it goes through, so you might have a better estimate there. Or in detailed routing, you might actually know it goes this particular layers, this direction, this many vias. You have a more detailed view. But in all those cases, you have a graph like this, and you compute the delay. And it's generally for optimization, I mentioned the incremental stuff, they use something very close to Elmore delay, because it's very fast and it's reasonable. For more accuracy, you can do higher order models, but that's kind of an option. Now, I do want to mention, when we talk about finding the driver delay, so let's say we have this first. I'm skipping a slide and I'll go back. If we have some gate driving some tree, we're dividing this into gate delay and wire delay, right? The gate delay is the delay from the input of gate S to the output of gate S. That's what we get from the table lookup. And to get that, we need two things. We need to know the output capacitance of gate S and the input slew. So we're going to assume the input slew of the inputs is available, and it comes from off chip somewhere, and so you can set it just a value. Now, what is this C effective? Now, it's actually not the simplest way to think about it is to sum up all of the capacitances that fan out from that driver, right? When we did the Elmore delay computation of a tree, you did that where you multiply each resistor times the downstream capacitance. So it makes sense to kind of do that and just say, okay, this capacitance is going to be C1 plus C2 plus C3, 4, 5. That's a little pessimistic because I kind of used the analogy before. You end up seeing a behavior of kind of this trickle behavior where when you drive something, it charges up the near side of the wire first and then propagates to the far part of the wire later. And kind of like the bucket fill problem, right? This is the thing I referred to last time, where it's like, oh, what bucket will fill up first? And it depends on the rate of something flowing out of a bucket versus into a bucket and so on. So it's a little bit of a problem. But the point being, the C effective is less than the total capacitance. And this C effective is what kind of determines the delay of the driving gate. So how much its output will switch depending on how much capacitance it sees at the start of the wire. And this is a concept called resistive shielding. So it shields the downstream capacitors from the driver. Now, the only reason I mention this is that when you actually look up in the tables, this is actually the C effective capacitance. So it's not necessarily the total of all the capacitors, it's some approximation of that. And Aaron, the TH127, he has a paper on actually using machine learning to predict the C effective of a tree. We actually just got accepted to a conference in April, I think. So yeah, that's kind of a cool paper because the algorithms to do are pretty complicated and a little slow. So once we do that, we can then figure out the delay of this driver gate, and then there's also different path delays through the tree in this case. If it's a single fan out, there's only one delay, but in this case, there's 3 different paths. Each of the fan outs of this tree have different delays and different slews, right? Because there's different wire lengths, and so different resistances, different capacitances, and you get different delays at all the outputs. These are the values that you'll propagate through static timing. So that's why when you have a wire, you'll have pins for these outputs of a wire as well as the input. You could actually have internal pins too in the static timer. But that's why, so this the graph I showed up here, you have, for multi-fan out wire, you have multiple pins like that. Now, how does it work from a high level? So what we're going to talk about is called block-based static timing analysis. It's actually based on a project management technique, operations research. You know, think about like assembly lines. How do you make assembly lines better? Well, you want to have parts arrive on a schedule, and it takes time to do things. You want to make sure everyone's busy all the time, no one's waiting. So they had stuff on that. And there's this 1966 paper called Program Evaluation and Review Techniques that inspired the first static timing tools. And basically the idea is it ignores the logic function, it formulates this graph, and we want to propagate the worst delays cumulatively from the inputs and outputs. And I'll go over some exact examples of this. So what are the worst delays? Well, we're going to start to use a couple terms. So these are terms that are used throughout the industry. All the tools use the same terms, so it's disciplinary vocabulary. So you should know this stuff. So the one thing we compute is called the arrival time of a signal. So it is effectively a delay from a start. What is the start? It could be the start of the clock period, right? The clock period triggers, and after the arrival time, that's when the signal gets to a point in my circuit. Now, we can define the arrival time, though, recursively based on the arrival times of inputs. So if we take a gate, for example, we can say, oh, if the arrival time of the A pin is 5 picoseconds and the B pin is 10 picoseconds, well, we know that the A pin has a different delay than the B pin. Remember, depending if it's in the pull-down stack on the bottom or top and some other things, you have different delays for different input pins. So let's say they're slightly different. We know that then the arrival pin of the top one is 5, has a delay of 25, and so that it would get to the output at 30. Now, the bottom path, though, if it arrives at 10 and has a delay of 30, you'll get to the output at 40. And so what we want to do is we want to figure out what is the maximum arrival time at the output of this gate. It's the maximum of either of those input pins plus the delay of the gate. So the arrival at the output would be 40. Right? Makes sense. Now, the thing that this doesn't mention is the slew. Because in order to compute these delays, you need to know the slew. So technically, there'll be some slew value here and some slew value here as well. But I'm kind of dropping that here, and then it'll compute the slew value out here as well. But for simplicity, I'm just showing it this way. Right? Pretty straightforward so far, right? What do we do in an entire circuit? Well, remember, we have a directed acyclic graph. We're going to do one traversal from all the inputs to the outputs. And again, remember, these inputs could come from D flip-flops. Now, if this comes from a D flip-flop, here I have the arrival time at all the inputs at time 0. If it comes from a flip-flop, what would the arrival time be? It would actually be the clock to Q delay of the flip-flop. Remember, that's the time it takes from the clock to the output of the flip-flop changing. So that's one difference here. I'm going to kind of just put that in parentheses, so clock to Q. But in this simple case, I'm just going to say, oh, it's all zeros. But it could be some tiny value. Now, we take all of those, and we basically do the same thing. We propagate through the circuit. Every case, we're basically doing the arrival time plus the delay. And here we're assuming all the inputs have the same delay, and we do the maximum at the output. And we can't compute, say, we can't compute the output of this gate until we compute this, right? Because we need to use that arrival time to compute. So it has to be a depth first, or a breadth first. It doesn't have to be depth first or breadth first. You have to complete the inputs before you complete the outputs. It has to be a topological traversal. That's the correct term. So you have to do things earlier in the topology before things later in the topology and compute all of the inputs before you process something. It's actually really easy to do, to sort everything topologically, and you do one iteration over all the gates in your design, and you have all of these computed. Algorithmically, in terms of CS, that's an O of n operation. Complexity matters, actually. This is where CS meets chip design. You do an O of n operation of my number of gates, so it's fast. And if I do that, I basically get the outputs here. The output of this thing is 100 units arrival time. I don't think anything else is too interesting here, but yeah, you have to do that topological thing. So topological order. Does that make sense? We're just basically repeating this for every gate such that we already have all of the inputs known values. And again, we would also do slews here as well, kind of glossing over that part of it. Now, here's the part where it's a little less clear, but it's kind of like a little less clear, like hold times are less clear, right? It's the same idea, but flipped around. We also want to compute something called a required arrival time. So what is a required arrival time? Well, I talked about the meeting example. If you want to show up for a meeting and you want to show up early, how early should you show up? Well, let's say I get into the office. I like to make a cup of coffee. I like to, put my lunch in the fridge across the hall. I have my stuff I have to do before I start working. And so that's my required arrival time. I want to arrive at least that amount of time earlier before I actually have to start. It's kind of setup time too, but yeah, that's how much I need 10 minutes to kind of get in my office and get set up. So how can we do that for signals? So we're going to first define this recursively, and I'll show you on that same example. Let's say we have a required arrival time at this input of this gate and a required arrival time here of 40 and 30. Now, it has to arrive at the signal on the top at 40 in order to make it the rest of the way downstream in time. Same thing with the bottom. It has to be there, such that by time 30, so that it can make it the rest of the way down the stream in time. Why are those different? Well, the top one has more stuff that goes through. That's why it's actually the bottom one. No, the top one can arrive later because it has less stuff to go through. Right? The bottom one has more stuff to go through and it has to arrive earlier. So there's a longer path down here, longer here and shorter up here. So that's why they're different. Now, how do we figure out the required time at this gate, at the output of this gate? Well, it's just the minimum, right? You have to arrive as early as the earliest time. There's no real way to phrase that other than that. Then, how do we figure out the required time of the inputs? Well, we just subtract the delays. So if they have different delays, the required time at the output is 30. If we subtract 5, it has to arrive at this input at time 5. The other one has a different delay, so it's 30 minus 30. This has to arrive at time 0. Someone's going to ask, well, what if it's negative? Well, if it's negative, it has to arrive before the start. That's probably bad. It's probably bad. Time 0 is the start of the cycle, right? So if it's negative, we already know there's going to be a problem. Now, I want to also point out that these delays for both the arrival time and the required arrival time, we actually do kind of a four-way computation. There's actually like a four-way table for all these, where we do rise, fall, early, and late. It's 4-tuple for the delays and a 4-tuple for the slews too. What is this 4-tuple? Well, we know rise and falls have different delays. You did the homework where we sized the gate so that it had roughly equal rise and falls. We know they're not perfectly equal. So that's why we compute it at every point. We actually compute the rising delay to that point, the falling delay, and also the rising required time and the falling required time separately. It's the same computation, except we just pay attention to polarity of the gates. If it's an inverting gate, you have to swap the input polarity, right?
Yeah. I'm just wondering why the top one is shorter and the bottom one is longer.
The required arrival time of the top one is later than the bottom one, meaning that it has less to do later, and so it can arrive later. So there's less path. Yeah, it's kind of what's downstream. The other one has to arrive earlier. The required time is earlier because there's a longer path downstream. And that's why it was less. Because every time we move to the left, we're having earlier and earlier required times. It's the way it's how think about it this way. The next slide we're going to go to. Well, let me do the computation of this first. We do the same thing for a circuit. So in this case, I'm going to say, oh, here's the required time at the output is 90. How do I know it's 90? Well, this might come from a flip-flop or go to a flip-flop. When does it have to arrive at that flip-flop? It has to arrive after a clock period, right? It's a setup time. What else? A setup time early, possibly some skew, right? All the overhead stuff. That's actually what this required time will be. It'll be t minus t setup minus t skew, etc. But we can just kind of cut it off and say, okay, set it to this value, which is that. Or if it's going off chip, you might set it to some arbitrary value depending on where it has to go. Not arbitrary, but some intended value. Now we can just do the same traversal, except now we do a topological traversal backwards. And here, why does it have to be topological backwards? Well, what if this one fans out over here too? Well, when we have fan out, we have to do the minimum operation. And I'm not showing that right here. But I'll show that. I showed it on the previous slide, right here. We have fan out, we go backwards. We have to know the required times on the fan out before we can figure out the required time at the output of that gate. Because otherwise you can't do that operation. But this one has no fan out. So what do we do at each stage? Well, if this is 90, and this gate has a delay of 20, we basically do 90 minus 20 is 70. So the required arrival time at this node here, and again, I'm ignoring wires here, so there would technically be a pin here, a pin here, and a pin here, where this would be 70, and then this one would actually be 70 minus whatever wire delay. But I'm ignoring wires, right? So we're just assuming that's the same. And then we have that 70 value. 70 minus 20 means the delay here and here is 50. 70 minus 20, right? So that's showing it there. And then again, I'm assuming 0 wire delay, so this is also 50. So that's just the assumption. And if we want to do this, 50 minus 60, the delay is 60. Well, here I end up with negative 10 and negative 10 required times. We got into that negative region, right? That's probably bad. But in the top path, we can kind of do the same thing. 50 minus 20, we get 30s. 30 minus 30, we get 0. So the required time at those inputs on the top is 0. Now, you can already tell the negatives are probably bad, but how bad and why and so on. Well, that's where we're going to define something called slack. So slack is like if you have a rope and it has to span a certain distance, and if you kind of move a little closer, there's slack in the rope, right? That's extra wiggle room in the rope length because it has to go shorter distance. Same thing with timing. If you have a schedule and you have kind of a schedule where it takes you so long to get somewhere, you want to leave before you have to be there and leave a little wiggle room so I can get used to my office stuff, right? You make my coffee and things like that. That extra time is slack. And so it's arriving earlier than necessary, but it's good. If slack is negative, that means you arrive late. You have those friends that always arrive negative 5 minutes on the time, right? And or negative hour. I love Brazilian friends that like to arrive like an hour late. I think that's a cultural thing. So they have a negative hour slack. But yeah, if we do this at every point, we can basically do rat minus at. And so at the output here, notice this had a slack of negative 10. What that meant is that output arrives at 100, but it's needed at 90, so it arrived 10 minutes too late from when it was needed. If we do that at every point, now we can actually do this in parallel, right? There's no ordering here because we already have all the arrival times, we have all the required arrival times. Just do the subtraction. Here, it's 80 minus 10, or 70 minus 80, negative 10. Notice here, it's 50 minus 50, slack of 0. That means we just made it to that point on time such that the downstream stuff would not be a problem. This bottom path, note that this also has a negative slack of negative 10, including the inputs that had a required time of negative 10 minus 0 is a slack of negative 10. Now, once you do this for all of your gates, you can look at the worst negative slack of your design. So that's a term also, WNS, worst negative slack. In this case, it's minus 10. And there's a unique property that anything that has any point in the circuit that has a slack of minus 10 is on my critical path. So I don't have to trace over any paths. I did this forward traversal, this backward traversal, and I suddenly know everything that's critical. Right? I don't have to do like a depth first search or anything and figure it out. There will be circuits where you could have more than one path that are equally critical and have this same negative 10 slack. There could also be some other paths that have, let's say, a negative 8 slack. What does that mean? Well, it's not the worst path, but it's pretty close. And if we fix that worst path, that's going to be the next one that's the problem. So now you have your worst path, you know your things that are close to being the worst path, and still would be a problem. And then you know your paths that have plenty of time. This path right here has 30 slack. I could delay that input 30 time units and it would not affect the performance of the circuit. That's great. If I want to add logic or do something, I can do that there. Yeah, so this gives you a bunch of insight. Now when you want to do optimization, it can also sort these things based on slack and then try to change and improve parts of the circuit that have that slack. Does that make sense? The key thing is 2 topological traversals, and then I know all my critical paths and how critical they are. That's why it's block-based timing, because you do those 2 passes, whereas some people mention path-based timing. That's where you have to do some sort of a depth-first search of this to try to enumerate the critical path by branching on paths that are the worst. Now, why would you maybe want to do path-based timing? Well, I'll get to that in a minute. Okay, I'll leave that as an open question. There are cases where you might want to. Now, I mentioned it a few times, but we typically do rise and fall for all these values too. The amount of data increases quite a bit, but the actual computations don't really change. If we have an inverting gate, like an inverter, NAND, NOR, a rising input will cause a falling output. If we have a non-inverting gate, like a buffer or an AND gate or an OR gate, a rising input will cause a rising output or no change for both of those. Right? The polarity kind of remains constant. So what happens is when we do the forward propagation, we just say all the rising inputs cause falling outputs, or all the falling inputs cause rising outputs if the gate's inverting, and vice versa. So it changes the forward traversal. It does the same thing for the backward traversal. You swap the entries in the table appropriately. So it doesn't add too much, but it does add a little more complexity. The one that's a little more confusing is early and late. But we talked about setup and hold times. Typically for setup times, you want to use the latest arriving things. You want to know the longest path to a flip-flop and check if that arrives before your period. What about the hold time? Well, there you want to know the fastest path. So actually, you're going to use the smallest delay for all the gates, not the largest delay. And you're also going to flip things around a bit, where at the output of a circuit, if we have a graph going here, and I set this required time, what is it going to be for a hold time? Well, it's not going to be the clock period anymore, because I want to consider the hold time to the same clock edge. So it's going to be basically clock skew plus hold, t-hold, or minus t-hold, actually. A lot of times it's just inverting polarities, but I want to make sure that the required time is after the hold time, but it also the skew eats away at it, so that could be a problem. And then when I go backwards in this case, I want to find the earliest time for the hold time instead of as well. And when I'm propagating the arrival times this way, instead of doing the maximum, I do the minimum. So I want to do the earliest times for arrival times. So for arrival time, I do the max for setup, and I do the min for hold. Other than that, the propagations are basically the same. Now, let's look at some of the STA commands. We got 7 minutes. This is perfect. I'll go over the commands, and then we'll do a demo next time. There's commands, for example, to set up the clock. These are standard commands in primetime, OpenSTA. Basically, they're part of the standard that's called SDC. So synopsis design constraints. Now, the reason I mention this is a lot of companies do filtering based on keywords and resumes, right? Put this on your resume if you know STA, because they'll be like, do they know synopsis? Oh, they don't know synopsis. Well, yeah, you do, right? And then all the concepts are the same. So, I kind of recommend people do that. So basically, there's one command to create a clock. You can create a clock with a given name. It can have a period. It's going to be in library time units, whatever your library's in. And then you apply it to a set of ports. So in this case, I have a variable in my Tcl scripting called clock port that it gets the port in my design, and it sets this clock up on there. There's also a command where you can set the driving cell of the clock. Now, why does this matter? Well, if I have a chip, and I have a pin coming in, what does my clock tree look like? Well, there's going to be some buffers and stuff, but what's driving it from off chip? Well, I'm saying there's something that's like a clock buffer size 2 from off chip. And so if it has a big fan out, it's going to have slew and all this sort of stuff. So you can set the input driving cell, which helps define that clock, especially the slew rate of the clock. You can also, if I ever have a path between, let me erase this and clear it up. So if this is my chip, if I now have any path between a flip-flop and a flip-flop, this command create clock defined what the required arrival time is for the setup check. Because I define that clock, I know the period, it can go there and it can say, oh, my rat for this gate right here is some value. Right? And I also know my clock skew as well. Like I can just propagate the delays through the clock tree and get that. Now, what about primary inputs? Let's say there's one input that comes here to that logic from off chip. Well, when does that input arrive? What I typically do is, or what you do is you use the command set input delay, which just sets a fixed value there, and it is relative to a clock. So it's as if it came from a flip-flop and went through some logic with a fixed delay. Now, why would you do that? Well, maybe it's coming from another chip. Let's say it's coming from another chip. A flip-flop on that chip has to go off the chip, onto the board, and then onto my chip, and then through a buffer, an I/O buffer, and then to my chip. That kind of delay will account for all of that stuff. It eats away at your clock period. You can also set the driving cell. In this case, I set it to an inverter, just because it's a small gate. Now, what about primary outputs? Same idea applies. So let's say we have logic here going off chip. Well, that's going to say it goes to a flip-flop off chip with some delay here as well. And it's going to be related to the clock, same clock, here, as here. And it's going to have some additional delay of 10. And I'm also going to set a specific capacitance on this pin as well, because we know delays are related to the capacitance it has to drive. So the three commands, the first one is basically flip-flop to flip-flop passed on chip by creating a clock, and then you do the inputs to flip-flops, and then the outputs to flip-flops to outputs. And then that defines all of these required arrival times of the outputs, input arrival times, and then the ats and rats for the flip-flops. Well, I forgot to mention that, yeah, this one right here, this would define the clock to Q delay would define the inputs of this one, right? Because that was from a flip-flop. So now I can do my timing analysis on that. Now, are we good? We got 2 minutes. I'm going to take off from there next lecture. That's a good place to end it.